Good morning. Today I'll be sharing the work that I've been doing for taming wild faces with a focus on web-scale open universe face identification, and this has been largely focusing on still and video imagery and how we can look at these problems. But first I'd like to define what are wild faces, and to do this I did a Google image search of some of the characters from the popular show Big Bang Theory. And so here you see some pictures of Jim Parsons, Johnny Galecki, and Katie Cuoco. And you can see that there's a large variation in pose, in lighting, and different sensors. But we can get even more wild than this. If we were to look at some of the images that we would see on Facebook, for example, you can see that there's an even larger variation in the pose, the illuminations, the different locations. You can see that the camera sensors themselves are very different than what you would see even in, when we're looking at these public figures, because the people that are taking the pictures aren't necessarily professionals. And so this is similar to what you'd see even on Flickr or Picasa. On Facebook alone, there's 350 million photos uploaded daily. And then we can even look further at one of these videos that I got from YouTube, and you see that there's even a lot of variation here. If we look at even on Google Play, this is very similar to what we would see Amazon and iTunes. On YouTube, we have about 100 hours of movies uploaded per hour, and on iTunes alone, there's about 60,000 movies. So this shows that there's a very large breadth of variations that we need to address in this open universe in this, on this wild data. And it also shows that there's a large room for automation via face recognition. So why are wild faces important? I'm going to frame this in the context of the three main tasks of face recognition. The first is closed universe face identification, and the idea here is that given a test image, we want to give it the correct identity. But in this scenario, your training dictionary, the names that you know, you never expect to receive anybody that's not within that training. Some of the data sets used for this analysis are the extended Yale B, where they look at variations in illumination, the Ferret data set that look at variations in pose, and the AR data set that looks at variations in expressions and occlusions. There's been some recent studies on a little bit more open wild data, not necessarily open but more wild data with the public figures 83. And finally in video we can look at the YouTube celebrities. The second task is open universe face verification. And the idea here is given an image of a person, is this who they say they are? And so this has been kind of casted as a pair matching task. So they look at same or not same pairs. The two popular data sets are label faces in wild and the public figures. And for video, it's the YouTube faces. And finally, the third task is open universe face identification. And this is the one that most interests us. Here we not only want to assign an identity, but also assign a probability of the existence of that person within your dictionary. So let's look at why this is important. If we were to look at this image, and we were a news article agency, we might be more interested in the public figures. So we would actually want to label Barack Obama while ignoring all the faces in the background. However, from a social networking standpoint, we would be interested in our friends. So we might label Bob and Alice here while ignoring all the rest. In terms of movies or video, if we were to look here, we would see that we could label Gwyneth Paltrow. If we watch the video further, we'd see that we're actually interested also in Robert Downey Jr. But notice that there's a lot of faces sitting and standing in the background that we'd actually want to ignore. These are people that are not of interest to us. From still image research, there hasn't been any public data sets released. There's been a lot of analysis from NIST. From video, there's been a couple with two from Buffy and also one from the Big Bang Theory. However, their emphasis hasn't been on this unknown, this open universe side, even though they have looked at it a little bit. So the problem is that the current data sets are small and ill-posed. And the problems that we want to look at are more real world, where we want to look at the open universe task, larger quantities of data, and also take into account that there are large variations in pose, illumination, and inclusions. So the rest of this talk is outlined as follows. We'll be talking a little bit about the related work. We present a new method for still image open universe face identification. Then we move on to video-based face identification, where we propose another method. And finally, we propose another layer to the video recognition system that's able to more consistently label the identities throughout a video. So for related work, face recognition can be divided into several categories, one of them being pre-processing, where we want to normalize for illumination, pose rectification, and even we could lump feature representations into here. The next is dimensionality reduction, where we want to reduce the dimensionality of the data so that the execution speed of the algorithms can be much quicker, but we want to represent the data with only the most useful information. And finally, we have classification, which is what we focus on. And here, we want to actually do the recognition task. Support vector machines have been very popular in most, in a large breadth of areas, even in face recognition, where we just feed it many features and it's able to do very well. However, we focus on sparse representation-based classification because they present a bit of a paradigm shift in the way that classification is done. The key idea is that we can represent a test image as a linear representation of the training gallery, and that the representation is sparse because you have very few images of the known person that you want to actually label, and many images of all the other people in your training. However, from the beginning, the drawbacks have been that it required perfectly aligned faces and that the classification is slow. So research in sparse representation-based classification has pretty much focused on these areas in the vision community. They've looked at the simultaneous alignment and classification. They've looked at estimating lighting and doing pose rectification at the same time. And they've also looked at using features, where one of the papers, the first ones was they applied Gabor features and were able to get better performance that way. There's been another area in dictionary selection where they're able to find a subset of the larger dictionary that they can then perform sparse representation upon, and this is kind of where our method lies. And finally, there are linear regression methods that have said, let's eliminate the sparsity constraint on this coefficient vector, and we'll talk about this more as we move along to see if in real-world data this is actually true. In video, there's different categories, one of them being keyframe-based algorithms where they actually select the keyframes from a complete face track, and you can label each of these individually and do probabilistic voting to find the final solution. However, we look at the whole face track in its entirety. There are also temporal model-based methods, for example, using hidden Markov models. But two of the papers that I looked at, they actually impose motion on a still image gallery. So this is a bit of a non-natural training, and it seems to be a bit expensive. There's also image set matching, where they use mutual subspace learning, where they're able to learn a subspace for each face track. They match, where they learn one for the first one and one for the second one, and they can map each to the other. And the ones that, if they match well, they would have a minimal distance. And finally, there's an area of person identification, where the problem is not only to recognize the person when their face is available, but you also use other contextual clues so that when they turn away, you're able to continue tracking and actually identifying the person. We focus on the classification portion because we believe that if you were to able to get this very high accuracy there, when you add the contextual clues, we could do even better. So next we move to our proposed method for still image OpenUniverse face identification, which was recently published in CVIU. So the problem that we're looking at is still image face recognition. And still image face recognition is that given some photos from Facebook, we have the tags that we can use for training, and we can use the face detections to do training. And then given a test photo, we can extract the faces, feed it into our system, and hopefully give the correct identity. Now, as we've mentioned before, sparse representation-based classification has two main drawbacks. The first, that it's slow and is sensitive to all the variations in pose, illumination, and occlusions. However, our solution is that we're able to use a simple combination of three features that address those sensitivities to all the variations. And our main contribution is fusing the speed of linear regression with the robustness of sparse methods so that we can get better performance. So our method is linearly approximated sparse representation-based classification. And we have as input a large training gallery that we'll call A and a test face Y. The first few steps that we do is do alignment using the eye locations, and then we do pre-processing to normalize out the illumination variations. We extract the three features that we use are local binary patterns, Gabor features, as well as histogram of oriented gradients. We perform PCA on these individually down to 512 dimensions and concatenate into one long 1536 feature vector. So now we move on to the main contribution, which is the algorithm, and we'll discuss these as we move along. So the main idea is that we want to represent a test image as some linear representation as a training gallery. So the most important thing here is that we want to find the most optimal representation, and so the problem here that we want to do is find this coefficient vector, x. So the obvious solution is to look at the least norm, and so what we do is we're actually minimizing the residual error between the test frame and its representation from the dictionary, while imposing an L2 norm on the coefficient vector, so that we can find a unique solution to this this underdetermined system. We can do this via the pseudo inverse, and the best thing about this is that it's very fast to compute. Therefore, and you can even pre-compute it and cache it, so that given a new test phase, you're able to just multiply it by this pseudo inverse and get the coefficient vector very quickly. Here I show an example coefficient vector that we get from an image from the control data set extended YLB. And you can see that the best matches are concentrated here at the beginning, and so you can see that by the magnitudes of the coefficients. The x-axis actually tells you the index into that training gallery. So even though it performs very well and quickly on control data sets, we found that it performs very poorly on real-world data. So what can we do? We know that the test image is represented by a few images that actually correspond to it within the training gallery, while the contribution from the others should be 0. Therefore, given a sufficiently large training gallery, this coefficient vector should be very sparse, meaning that you have a few non-zero values and the rest are 0. So what sparse representation-based classification does is proposes imposing the minimization, the same minimization as before, but imposing an L1 norm on the coefficient vector, which emphasizes sparsity. Now the classification is performed by computing a per class residual error. So the minimum residual class-based residual error is the best match. However, because we're kind of analyzing this open universe scenario, we need a rejection criterion. We need a way to determine whether this person exists in our training gallery. So this is based on the sparsity of the coefficient vector, and what the equation tells us is that if the reconstructed coefficient vectors are concentrated in one class, then we probably have a good reconstruction. But if they are distributed across all the images in the training gallery, then you probably have a poor representation. So here's an example of the sparse vector that's reconstructed, given the same image that I showed earlier, and you can see that it's dampened out most of the noise that we saw in the previous one, and we still have the high peaks here at the beginning. We found that it not only works well in control data, but also the real-world data. However, it still is computationally very slow. So what we want to do is motivate approximating this this sparse coefficient vector. To do this, we look at the Lagrangian formulation of the L1 equation, where we're minimizing the residual error between the test frame and its representation in the dictionary, and imposing sparsity. What this lambda tells us is how much weight we want to give to that sparsity. So if we write the objective function as follows, we can continue to motivate this approximation. If we represent this as in vector notation, we get the following equation, where it's a multiplication between the vector scalar, and what we want to look at is if we knew which indices are the ones that correspond to the non-zero values within that coefficient vector, we could define a new vector called alpha and omega, where it has the corresponding dictionary elements. So we can write a new objective function where we relate omega and objective and alpha in the same way. If we look at these two objective functions together side by side, we can know that if we knew what those zero coefficient values were, the two objective functions would reduce to the same equation, or the same solution. So we can reformulate the L1 minimization as a minimization of the the residual error between the test frame and its new representation from this subdictionary. Now the problem is that we need to find out what this subset is. But given a sufficiently small subset of the total dictionary size, which is n, we could speed this up greatly. So what I want to propose is that the L2 norm solution can be a good approximation. So if we look at the original equation, we can see that the highest peaks are concentrated within a certain region here, especially on this control data. We can see that it actually matches to the same peaks in the L1 solution. So what I'd like to say is that the shape is very similar, so we could use the L2 norm to approximate the L1. So what we do is we actually, given our large training gallery and our test image, we first find the L2 norm coefficient vector. We select the largest magnitudes and select the corresponding training images, which we then feed into the L1 minimization to find the final coefficient vector, from which we can compute our confidence as well as the final identity person of interest. In order to analyze this open universe context scenario, we propose two data sets. One's public figures plus labeled faces in the wild, where we take two existing data sets and combine them so that we can evaluate unknown identities, and then we collect a new data set from Facebook. Here's a small sampling of the public figures plus LFW data. You can see here there's a large variation, however the type of pictures are pretty similar because the camera sensors are more professional. The thing that we did was we took the public figures and used it as the known people that we want to train on, and the unknowns are selected by the non-overlapping identities from the label faces in the wild. What this results in is 200 identities with 44,000 training images, 11,000 testing, and 11,000 unknowns. For the Facebook dataset, we have a small subset here. And what we did was you can log into Facebook, download the pictures, and you can get the tags from them. We match them to face detections, and this allows it to automatically, in an automated way, actually get a data set for testing. What this results in is real noisy data that we'd see out in the wild, and so you can see variations in lighting, blur, expressions, occlusions, and some missed detections. So we create three data set sizes that mimic having different numbers of friends. The first being a group of 256 friends, and this results in about 25,000 training, 8,000 testing, and about 4,500 unknowns. We doubled this number of friends to 512, which almost doubles the number of images for each of these categories, and then we double it again for a total of 90,000 training, 30,000 testing, and almost 1,900 unknowns. So we first look at closed universe metrics because it's the standard, and so we look at accuracy, but we're more interested in precision and recall. And so what we do is we actually threshold out the people, the unknowns, as I don't knows, using our sparsity concentration index, and for different algorithms we might use the probability of its confidence in its prediction. We use the same metrics used for recognizing TV characters in the Buffy paper. And what they define recall is the percentage of known faces that are assigned an identity, and the precision is how well we do on those images that we assign an identity. So the results can be summarized into three types. We have where we analyze the feature representations. Then we look at sparsity versus locality to see if we can drop that sparsity constraint. And then we compare to the state-of-the-art with our two data sets in Facebook and the PubFig plus LFW. So first, let's look at feature representations. Well, we find that if we use this simple combination of the three features that are PCA, and we feed them to any of these classification algorithms, on the extended YLB, almost all of them get close to 100%. And the same is true for the AR data set. So we can use these to benchmark our algorithms, but this shows that we've pretty much saturated these data sets, and we need to start to look at the problems that we would see in more real world, where all of the variations that you see in these data sets are all combined. Next we look at sparsity and locality. And so as I mentioned before, there's been some research where it says that this L1 constraint is not necessary. And so the first paper on real-world Facebook data, what we were able to achieve wasn't very good. So then we looked closely and we saw that if we balanced the data to a maximum of 100 images for the training for each of the training people, you actually get a better response. Then we looked at threshold at L2. And what this does is actually the first stage of our LASRC algorithm. And you can see that the performance is improved even further. But when we add our L1 constraint to this, we see that we can even obtain even further improvements. So this kind of confirms that, especially for real-world data, the sparsity constraint actually helps to reduce some of the noise. Now in comparison to the state-of-the-art, we look at the PubFig plus LFW results, and I compared to several non-real-time algorithms. This could be either in training or testing. So SVM is considered non-real-time in the sense that it takes a long time to train on our large amount of data. However, the SRC algorithms take a long time for testing, even though they obtain the best result in terms of accuracy as well as recall at high precision. However, if we look at our real-time algorithms, LASRC performs the best of those, but also has a very quick test time. So we were able to get the speed and performance that we were looking for. Now we look at the Facebook precision and recall curves. And the brown curve represents our algorithm LASRC, and we see that it's able to classify 55% of the data at 95% precision. However, even though LASRC, SRC, and SVMs perform very similar to each other, we can see that LASRC in terms of training time, in testing time, performs better than SRC, but SVM and better in training compared to the SVMs. So in summary, for still image identification, we present a motivated method for fast real-world face recognition. We present a new real-world data set from Facebook, as well as the PubFig plus LFW for evaluation of OpenUniverse Metrics. For very large realistic data sets, LASRC is 4% better than SVMs at high precision, and is 40% faster than standard SRC. So next we look at how can we extend sparse representation-based classification to the video paradigm. What we're interested in is, given a video, we want to track a face, but not only that, we can take an annotated library of still images, feed it into our algorithm, and output the correct identity. Here's a complete pipeline of our system, where similar to before, we have a still image gallery A that's inputted to the system, but now we're looking at video. So given a video, we actually perform face detection and then do tracking. We use two simple metrics for this. The first is an appearance-based metric that does a histogram intersection of the 3D color histogram from a frame. The second imposes a spatial constraint where we know that the bounding boxes should not be jumping from one side of the frame to the other. Therefore, they should have a large overlap from frame to frame. Here's some qualitative results where the red bounding box shows our ground truth and the green shows our tracker. You can see that the tracking is very smooth, especially here where the faces take up a large portion of the frame. For quantitative results, we manually annotated 5 movie trailers, and we look at the multiple object tracking precision and accuracy metrics. We find that compared to one of the popular methods, which is a feature-based method, we're able to get similar precision and accuracy. However, our method results in a 3.5 times speedup. Next, we do similar processing that we do before. We do eye alignment, then we extract 3 features, LBP, Hog, and Gabor. But here we actually do PCA to 1536 dimensions because we found it worked better for this scenario. However, our main contribution is in this extension of SRC that we call mean sequence sparse representation-based classification. It takes as input all of the frames from a given face track. As we saw before, the standard formulation for sparse representation minimizes the residual error between the test image and its linear representation from a dictionary while imposing sparsity on that coefficient vector. However, we know that we have multiple frames from a video face track, and so we need to make some crucial assumptions. The first that we make is that the frames are highly correlated, meaning that all the frames within a face track are of the same person and they have a similar appearance. So we make this strong assumption from this that they should all agree on one common coefficient vector. So if we were to extend the L1 minimization to video, what we would do is minimize the residual error over all of the frames within a face track, while still imposing sparsity on the coefficient vector. Now what we want to see is what does this equation reduce to. And we can see that if we were to focus on the first portion here, and we add and subtract the mean, we can use this linear algebraic expression. If we look at the central component here, and we move the summation into the parentheses, we can see that this reduces to the mean minus the mean, so it goes to 0. So what we're left with is a constant which doesn't contribute to the minimization and the minimization of this residual error. We can absorb this m coefficient scalar into the lambda in the original equation to result in the following, where we're actually minimizing the residual error between the mean vector, the mean face vector, and its representation in the dictionary, while imposing sparsity on the coefficient vector. So for recognition, we actually do similar computation where we do a per class residual error to find the best match, and then we use our confidence based on the sparsity concentration index. We collected a new data set to evaluate this OpenUniverse scenario, and so what we have is 101 movie trailers that we downloaded from YouTube from the year 2010. What this results in is about 4,500 face tracks, and a small sampling is shown here. Of these 4,500 face tracks, about 1,600 of them are tracks from people in the dictionary, and on the left what we see is a distribution of the number of face tracks to the identities in the dictionary. So we have 210 identities. The dataset consists of the public figures dataset that's been supplemented by 10 more people that we did a Google image search on. Here are some of the qualitative results, where the people of interest are Paul Rudd and Steve Carell. You can see that they're correctly identified while also labeling the unknown people correctly. Here, Katherine Heigl is labeled correctly, as well as the unknown villain. For quantitative results, we looked at several algorithms, and the first is nearest neighbor. So we actually took the face track and we classify each of the frames using nearest neighbor and do a probabilistic voting. And you can see that it does very poorly. However, we moved to do the same thing, but we actually introduced the support vector machine. The average precision and the recall at high precision actually increases very quickly. We also tested metric learning, and we found that it didn't do too well here because it was trained on a still image gallery and then tested on video, and it didn't do very well in that scenario. We also compared to eliminating the L1 norm, and you can see that it doesn't do better than support vector machines, although sparse representation-based classification with just one frame is able to do better. Now what we look at here is, instead of using an SVM or a nearest neighbor, we use sparse representation-based classification for each frame in the face track, and we can see that it actually obtains the best average precision and recall. When we introduce our method, MSSRC, we're able to even outperform that because it's able to average out many of the errors. However, we can get a 5 times speed up over SRC because we only do it once per face track instead of for every frame within a face track. Now the next question is, what happens if we were to combine LASRC from the still image optimization and MSRC from the video? And we can see that if we were to use all of the frames in our training dictionary, you'd have it would take about 211 seconds per track for the minimization. However, if we reduce it to a third of the data, we would only lose 2% in average precision, but we get a speed up for 69 seconds per track. So in summary, for video face recognition, we present a complete end-to-end system from tracking to recognition. We present the new movie trailer face dataset for evaluation of OpenUniverse video face recognition. We propose a simple yet efficient tracker, and we show state-of-the-art performance on face identification while rejecting unknowns. So although MSSRC does very well, we have an extension that's able to smooth the results across a video for more consistent identification. So the problem is, if we were to here see and look at the output of MSRC, you can see that Melissa Rock was actually labeled incorrectly at the beginning and also here in the red. So what can we do? Given this video, we can make the observation that the video face tracks within a scene are very related visually and temporally. So if we had global knowledge, we could actually share that information across all of the similar face tracks. And to show this, you can actually look at this sample graph here, and you can see that I generated from the movie Date Night. And you can see Steve Carell's pictures are all related, and you can see that they are very related via this strong edge. This was automatically generated with our method, and then the unrelated face has a weak edge. So what we propose is a two-stage algorithm where we first do initial recognition using MSSRC, and then on top of that we do affinity-based propagation, where we actually encode the relationship between all the face tracks within a scene or even a video so that we can share the information throughout. We use 3 affinity metrics, where the first is an appearance-based metric. We use match background similarity metric, which was very popular and were very successful in the face verification task. And the idea is that given a face track I and J and a background set of images, you can use nearest neighbor between this face track and the background to get a subset I and J for each separately. Then you train a support vector machine using this background set and its respective track to get model I and model J. Then you can test the ith track with the jth model and vice versa, which will give you SVM scores that can be averaged to find the best match. So the idea here is that if they're very close to each other, they'll have a very small classification error. The next we look at is the coefficient affinity, and here what we use is that we use the knowledge that's given to us by the initial prediction from MSSRC. So we have the coefficient vectors I and J from MSRC, and we compute a cosine distance. And what this tells us is that if two face tracks are very similar to each other, they should be reconstructed from similar contributions from the dictionary. Next we look at the affinity, and we also use the output of MSRC, where we look at the labels for each face track and the frequency of these labels in this particular scene. We compute a normalized Google distance, which is able to tell us to encode the frequency of these labels and the co-occurrence of the labels. Essentially, if they co-occur often, then you should increase their edge. Next we do affinity fusion, where we fuse all 3 of our affinities by using the alpha values and then also smoothing them using a Gaussian, and the smoothing term is the sigma here. For our experiments, we found that just holding the sigma at 1 worked very well, but we did optimize the alpha values via a greedy search. So given this fused graph, we can actually normalize it by the sum of the rows. And what this allows us to do is to treat each of these values as a transition probability from the surrounding nodes to each other. So next we actually look at how can we propagate these labels from the surrounding nodes. So given a node I, we know that we have a contribution from all the nodes that are around, and we can code this by the transition probabilities that we computed via the affinity matrix A. To encode this, we can say that it's a weighted summation between the initial prediction of the node and the summed contribution from the surrounding nodes. We can show this as a matrix vector multiplication, and we want to do this, improve this solution iteratively as we go along in our search. However, we can show that the iterative method has a unique solution. What this allows us to do is that we can propagate the probabilities in one step for all of the nodes, and then we can select the most likely identity by maximizing that, finding the maximal probability. We then propagate these confidences of the sparsity concentration index, which we use to then threshold out the unknowns, as we've done before. So to do this, we use two data sets. We use the Big Bang Theory data set, which was released recently, last year, and it has about 3,800 phase tracks, and 415 of them are unknown. We have 11 actors that we want to recognize. And so as I showed, this was the before picture of this scene. You see there's two errors where Melissa Rock is labeled incorrectly. But if we move on to after propagation, you can see that those errors are corrected. Now we're able to also do quantitative analysis because in the paper that was released, there are 6 episodes of Big Bang Theory that have been annotated, and their average result was 83.71 using a maximum linear regression as well as an MRF. Now if we use just MSRC, we're able to get almost a 2% improvement over their method. However, if we combine it with the affinity-based propagation, we get close to 4% increase over the state-of-the-art. Now we look at our movie trailer data set, and here I show an example graph that I generated from the date night movie trailer. And you can see in these green regions, the circled green regions, that there are some errors within those regions that you can tell, like you would probably guess I should label them as Tina Fey or the blue node. And then there's a couple of Steve Carell as well, but they're not as obvious as the Tina Fey ones. With our affinity-based propagation, we're able to correct those nodes and obtain better results. So we can actually look at quantitative results for the movie trailer face data set. And we actually look at accuracy, average precision, and recall at high precision, so at 90% precision and 95% precision. And these were the results that I presented before for MSSRC, which were already the state-of-the-art. However, if we introduce affinity-based propagation, we can improve this further. You can actually, because there's those optimization parameters, you can actually optimize for different metrics. So you can optimize for the best accuracy, where fusing all 3 of the metrics results into almost a 34% increase in accuracy. Then you can optimize for average precision, which is about 13% increase in average precision. And then maximize for high precision, where you can see it's between 6 to 17, or 11% in increase. Also, you can actually look at the contribution from each of these individually, and you can see that each of them provide their own benefits. If you want speed, the best to use is the coefficient affinity because it computed very quickly after the MSSRC, and it actually results into similar average precision and recalls at high precision. So in summary, in this dissertation we've explored OpenUniverse face identification. We released 3 new data sets, one from existing data sets combined so that we can look at these OpenUniverse metrics. Then we look at the Facebook data set, which was automatically generated from the social network. Then we collect the movie trailer face data set from YouTube for OpenUniverse face verification as well in video. For still image identification, we propose a new method, LASRC, that performs equally to the standard SRC method with 100 to 250 times speed up. And for video-based identification, we present an algorithm MSSRC with 5 times speed up that already in itself had the state-of-the-art performance. However, if we add our global affinity-based propagation algorithm, we're able to improve that average precision by a further 15.8%. So some of the future work that I would look at in still image, especially in regards to still image identification, is that I would look at if we could do dimensionality reduction in tandem with LASRC. So you could even do it at the linear regression step and have an optimal reduction so that we can then feed that into SRC, and that would give us an even further speed up. Because we found that reducing the dimensionality of the data not only had computational benefits, but actually gave us better results than using the raw features. I would further explore, so related to this, explore feature representations that are specifically geared for sparse representation-based classification. And finally, we can obtain further speed improvements via multi-threading and GPUs. For video-based identification, in this context that I was looking at, there's a domain transfer issue where the quality and the type of sensors that are used for taking the pictures is very different from that we use for our training to the videos that we're actually testing. So you could actually probably get a better, even more improvement from that standpoint. I also would like to explore the effect of non-frontal faces on sparse representation-based classification. It shouldn't work. So faces that go all the way to an extreme 90-degree pose. I think that there's methods that would impose sparsity but also be able to address the issues from non-frontal faces. And finally, I would look at a joint optimization for MSSRC and affinity-based propagation. Right now we're doing it in this two-stage approach, and it would be more efficient to actually be able to do them in tandem in one step. Here's a list of my related publications, and I'm open to questions now.